Hello, we're back. It's video 21. This is about correlation. Guess what? Correlation is easier to understand and deal with than tests of proportion. You're welcome. I'm going to move this up here because in a second we're going to make some plots. But first I want to talk to you about what correlation is, kind of conceptually. So I think you probably know it, right? You've talked about correlation in a variety of ways, in a variety of settings, in kind of metaphorical ways, right? You're like, oh, something in the world is correlated with some other thing in the world. Basically, correlation in this class, correlation is a measure of the linear association, and linearity is going to be important, between two variables that are continuous, count, or sometimes ordinal. The result, the actual measure we get, is called the correlation coefficient. And the correlation coefficient can range from -1, which is perfect negative correlation, to +1, which is perfect positive correlation. And 0 indicates no association. So I want to carefully distinguish the correlation coefficient from the slope, because you're going to see some plots in a minute that are going to kind of make your brain try and think that the slope and the correlation coefficient are similar. They're not. So a line with perfect correlation, sorry, I'm trying to figure out what the geometry is with my webcam. A line with perfect correlation can have kind of this slope or this slope, this slope or this slope. Correlation can tell the difference between a positive and negative slope, but it doesn't talk about the size of the slope in particular. So there are kind of two axes on which we characterize correlation. Correlations can be positive or negative. That is, in positive, that's when X goes up, Y goes up. Negative is when X goes up, Y goes down. And they can be, weak, medium, or strong, kind of. So we talk about direction, positive or negative, and we talk about strength. An important caveat is that even very strong nonlinear relations are not going to show up in a correlation coefficient. So let's see what I mean. You don't need to open R. I made this so that I can kind of show you some graphs. Let me make this video and make this graphics pane nice and big. So what I've done here in cores.r is first make just a totally random variable called x. And x is going to be the independent variable, the x-axis, in every one of these plots. Now I made x, y1 and y2. Y1 gets x, that is to say y1 is equal to x, so that's going to be a perfect positive correlation. Y2, negative x, a negative correlation. Y3 and 4 are very strong positive and negative correlations, so they're equal to x or negative x plus a sort of small error term. 5 and 6 are strong but not very strong. 7 and 8 are weak. And you can see the kind of the thing that's causing the strength of the correlation to change is that I'm adding more variability in the error term. So for instance, there's no error term for y1 and y2. For y3 and y4, the standard deviation of the error term is 3. 5 and 6, the standard deviation of the error term is 10. You don't really have to know that. This is just to make some graphs for you, but it's useful. And then the last two are two non-correlated variables. So y9 is a completely independently produced random variable, so it should just make a cloud. Y10 has a strong relationship to x. It is in fact x squared plus an error term, but because it's not linear, it would show up with a correlation of essentially 0. So line 14 there is a way to set up multiple plots in one window, in case you're wondering. And then all of these are just scatter plots. So in all of these, x is going to be on the x-axis, and the different y's are going to be on the y-axis. Okay, let's look. Source. There they are. So they're showing up a little bit small here, so I'm going to make them a little bigger. I'm going to try to make them a little bigger. And basically that's what we're seeing. We have, so here's in the top row, we have perfect positive and perfect negative correlations. In the second row, very strong positive and then negative correlations. In the third row, strong but not, amazing. In the fourth row, extremely weak correlations. And in the fifth row, one correlation that is zero because it's truly unrelated, and one correlation that's going to come out to be zero because the relationship is not linear. So even if there's a clear relationship, it might be a perfect relationship. If it's not linear, correlation is not the right test. And that's a useful and important thing to remember. It's also going to show up again when we talk about linear regression assumptions. And I want to make note of the fact that it can be actually really hard visually to tell the difference between a weak correlation and no correlation at all. So the best way to test is to say COR. Whoop, come back. There we go. So I'm going to go COR x comma y1. And that is, of course, 1, because x is equal to y1. Likewise, when we do core x comma y2, we should get, yes, -1. Core x comma y3, 0.96. That's an extremely strong correlation, much stronger than we typically see in political science. Y4, -0.96. Oops, y5, 0.7, still quite strong in political science terms. So I guess what I'm pointing to here is that it's always important to actually do the correlation test because you can't always see visually what's going on. Let's finish these out. X comma y7, right? So we go from, here's in the third row, we have correlations of about positive and negative 0.75. In the fourth row, we have correlations of weak correlations, positive and negative about 0.21. Let's see, x comma y8 for x comma y9 should be, so this is fifth row, first column, should be basically 0. Yes, tiny. So there's a very small random negative correlation. Likewise, even though x and y are clearly related, we get a very weak correlation number for core x comma y10. And that again is because the true relationship is not linear. And that's all I have to say about correlation. Again, positive versus negative, weak versus strong, always linear. The end.